In this video, we're going to pick up where we left off with Le Chatelier's principle, and we're going to be worried about temperature. Before we do, I want to just remind you that in the last video we said if we add a chemical that's in the gaseous state or aqueous state, that chemical has a molar concentration, and if we added it, it's going to be used up. So let's say that if we added CCl2F2 to the system that we have here at equilibrium, by increasing the concentration of that, the reaction is going to shift to the reactants to use up that extra chemical. If instead we removed, we'll say the same chemical, CCl2F2. So if instead we removed this chemical, there are fewer of the reverse reactions and relatively more forward reactions. So the reaction shifts to the products to replace the chemical that was removed. So we're going to use that same kind of logic, though, in the discussion about how temperature affects equilibrium. Now, before we get further into it, I want to be clear. The only stress that changes the equilibrium constant, Kc, is a change in temperature. That's the only thing that can change that number of Kc. So in the previous video, when we talked about adding chemical or removing chemical, that doesn't change the Kc value. The Le Chatelier's principle says that it's going to shift to use up the chemical added or shift to remove the chemical used up, but it gets back to that Kc value as long as the temperature is the same. But now temperature can change the Kc. And what we want to do as background information, just as a reminder, is in thermochem, we had if the enthalpy is a positive value, it's endothermic. If the enthalpy is a negative value, it's exothermic. And if we had A plus B makes C. If this is an endothermic reaction, then we write energy as a reactant, right? So this is an endothermic reaction. If A plus B made C and this was exothermic, the energy would be written as a product. And we need to see this relationship before we can talk about Le Chatelier's. Because we need to treat energy like it is a term in the reaction, either a reactant or a product. And if I heat the system up, the energy will either be considered a reactant or a product. And if I heat it up, what's going to happen in Le Chatelier's is the energy is going to get used up. So if I heat a system that is endothermic, the reaction shifts to use up the heat. If I heated an exothermic, it'll shift in the reverse to use up that heat. If I cooled a system down, it does the opposite. I'm removing energy by cooling it. So in an endothermic system, the reaction would shift to replace the heat. And in an exothermic reaction, if I cooled it down, the energy shift, or the reaction shifts to replace the removed energy. So, temperature. We consider energy as a reactant or product, just as I indicated. An increase in temperature is adding energy, and cooling is removing energy. So that's done as an external force. If the reaction is endothermic, energy is a reactant, and if exothermic, energy is a product. If we heat up a reaction, we add energy and force the reaction to use up the energy in the reaction. So, in this reaction that we have here, you can see that this is an exothermic reaction. If I heat this reaction up, the reaction will shift to use that heat. If this is cooled, the energy needs to be replaced, it's going to shift to the products and use it up. And that's our basic move for all Le Chatelier's principle when we are deciding it. Once I know if this is going to be endothermic or exothermic, write the energy as a reactant or a product. Then, if it's heated, it uses the energy up. If it's cooled, it replaces the energy. Now, when it comes to graphs, it's a little harder to spot. So before we had one chemical that suddenly increased or suddenly decreased. But in a heating situation, we're not actually adding a chemical to it. Instead, we're changing the temperature. So these systems, or these chemicals at equilibrium, not one of them changes suddenly. There isn't like a sudden vertical line in our diagram. Instead, what we're going to see is the reactants and products doing opposite things. So here, I've got you can see that my sulfur dioxide is going down. My oxygen is going down. So it's shifting this way. My sulfur trioxide increases. So obviously my shift has gone this direction. So I've done something to make this shift to the products. When I go back here, I see that this reaction is exothermic, right? So this should have plus energy here. Now, if it has shifted to the product side, so I've used up the two reactants and made the product is shifting this direction, then the energy must have been removed. This was cooled down. And if I look here, it says the reaction establishes an equilibrium that is disturbed at the time indicated by a decrease in temperature. It was cooled, and I know that because it shifted this direction, and it's an exothermic reaction. So when I look at these graphs, if I see the reactants and products doing opposite things, but there's no sudden change in concentration for one of the chemicals, then I'm assuming that this is a temperature change because they're doing opposite things. Now, let's talk about the Kc here. If I were to write the equilibrium constant expression for this, so if the equilibrium constant expression for this is sulfur trioxide squared over sulfur dioxide squared times oxygen raised to the power of 1. If I am increasing the sulfur trioxide and reducing these two, sulfur dioxide and oxygen, is my Kc going to go up or down? Well, I'm making a bigger number in the numerator and smaller number in the denominator. Kc is increased in this situation because I'm getting more products and also getting less reactants. And so when a common question is, does the equilibrium constant increase or decrease in this situation? We'll look at volume and pressure in the next video.